Analysis of stability and diagram of bifurcation. To analyze the stability of the system, 6, 7, we firstly transform the system of two differential equations of the second order, 6, 7, to the system of four differential equations of the first order. We have noticed that 6, 9, is invariant under the transformation phi I plus 2 pi. As a result, every solution, phi I vertical bar greater than pi we can identify with solution phi I equals phi I mod 2 pi. The equilibriums of 6, 9, are given by phi 10, phi 20, 0.0, where phi 10 and phi 20 are solutions of the following algebraic equations. Since system of equations is nonlinear, we cannot find solution analytically, but we can do it numerically. We found that for each base pair there are 4 equilibrium points. Only one of them being stable, as all eigenvalues of the Jacobian of the right side of 8, 11, have negative real parts. It is P4 at equals 0.2753, 0.3347, 0.0, 0.0, point in the case of at base pair, and P4 GC equals 0.1658, 0.1658, 0.0, 0.0, point in the case of GC base pair. Below we present the diagrams of bifurcation of the analyzed system. In general, diagrams of that type show possible equilibrium points or periodic orbits of a system as a function of one of the parameters of the system. For every value of that parameter we can choose many initial conditions and find the trajectories. If trajectory is attracted to the stable equilibrium, we obtain only one point in the diagram. If trajectory is approaching to periodic, or quasi-periodic, orbit, we obtain 2, or more, points in the diagram. If each trajectory is attracted by different point, we obtain a lot of points in the diagram, which mean a chaotic behavior of the system. Bifurcation occurs when the change of the value of parameter causes the changes in the behavior of the analyzed system. In Figure 24, A, B, we present the bifurcation diagrams as a function of K01 parameter, describing the external force. Because we assumed that the external force is constant, the increase of value of K01 parameter does not change the dynamical properties of the system, in both, at and GC, cases, and we do not observe the bifurcation. It is worth to notice, that bigger value of K01 corresponds to the bigger displacement of the bases from the 0.0, equilibrium position. In Figure 24, C, D, we present the bifurcation diagrams as a function of B01 parameter, describing the parameter of dissipation. For very small values of B01 it seems that there exists some periodic or quasi-periodic trajectory, see Figure 25. Diagrams of bifurcation. In fact, trajectories are very slowly approaching to the stable point, and in the bifurcation diagrams we observe transient state of the system for small values of B01 parameter. For bigger values of B01 parameter we observe one solution for each value of the parameter. It means that trajectories more rapidly approach to the stable point. In Figure 24, C, D, we can notice also, that for each base pair there is a different equilibrium point, which is in agreement with our calculations. Trajectories in the phase space, phi, gamma, calculated for A, T, G and C bases and for the case equals 0.05 and F0,